Low-discrepancy sequences are sometimes called quasi-random sequences, although they are not random and don't look random. They're used for various purposes, such as high-dimensional integration and simulating financial option prices. I'm going to show you two kinds of low discrepancy sequences, the Richtmyer sequence and the Halton sequence, and how they are scrambled. Both of these are based on prime numbers, whereas there are other sequences such as Sobol, which are based on powers of 2. This is a low discrepancy sequence which doesn't look like one. It looks random, although it isn't. With smaller numbers, though, the sequence fills space better. The power scrambling for Halton with large primes produces what looks like random but isn't. This is a 5 versus 3 Richtmyer sequence. Richtmyer sequences are based on irrational numbers. A common choice, and the one used by the Quadlodes library, is the square root of the prime, or a slightly modified square root of the prime, because quadratic irrationals have bounded continued fraction terms, and thus do not get into the sort of uneven filling that you would get with, for example, pi, which is very close to 355 over 113, after only a few continued fraction terms. In Quadlodes, the primes that are congruent to 1 mod 4 are used with the square root of the prime plus 1 divided by 2. The reason is that the number that best fills the line, the irrational number, is the square root of 5 plus 1 over 2. Now, in quadratic number fields, if the prime is congruent to 1 mod 4, as 5 is, you have to include the square root of prime plus 1 over 2. Whereas, if the prime is congruent to 3 mod 4, you don't. Halton sequences are made by expressing an integer in the prime base and then reversing its digits. So if you're counting up and you get to 17 and you're using base 5, 17 is 3, 2 in base 5, so you would pick the rational number that is 0.23 when expressed in base 5. These two rational numbers, the one in base 5 and the one in base 3, are then plotted against each other. 41 and 29 give an interesting looking plot. It looks like a bunch of straight lines parallel with slope square root of 8. The reason is that 41/29 is very close to the square root of 2. A way to show what one dimension of a low discrepancy sequence looks like is the flower plot. This is so called because if you do it with the square root of 5 plus 1 over 2, the golden ratio, you get a pattern that looks like the arrangement of flowers on a sunflower head. This is what I call the Asteraceous pattern, from the family to which the sunflower belongs. The way this is plotted is you plot the number from 0 to 1 as the angle from 0 to 2 pi, and the radius is the square root of 1/2 more than the index number starting from 0. That gives each point approximately the same area in the plot. Another flower plot that looks well distributed is the Halton plot of 2. Halton flower plots are always counterclockwise out, except for 2, and feature broken Richtmyer spirals, which is easier to see with more points. If you look here and here, you can see where the spiral breaks. Whereas Richtmyer flower plots spiral in alternating directions and are equal angle points along the Richtmyer spiral. The Richtmyer spiral is the plot of the angle increasing steadily while the radius increases as the square root of it. Large twin primes cause problems for both Richtmyer and Halton, especially the primes that are 2 and 4 more than a square. Of course, 5 and 3 are 2 more and 4 more than a square, but they are small, so they don't give this problem. But 3,251 and 3,253 have to scatter. Give close to a straight line for both Richtmyer and Halton. The reason they give this for Halton is simply that they are close together. The reason they do this for Richtmyer is that the continued fraction terms of the quadratic irrational are all large. The terms of square root of 3,251 plus 1 over 2 are 57, 57, 114, 57, 114, and so on, whereas those of square root of 3253 are 29, 57, 57, 57, 57, and so on forever. These being very close means that the plot is close to a straight line. They get even closer to a straight line as the numbers get higher. 4096. This bunch of dots is an artifact of 4096. If I go up to 65,536, it turns into a bunch of short diagonal lines. Next pair of primes, 21,611, 21,613. 59,051, 59,053, even closer to a straight line. 65,027, 65,029. That is hard to distinguish from a straight line. These primes are 2 and 4 more than 57 squared, 117 squared, 147 squared, 243 squared, and 255 squared, and their continued fraction terms correspond to those square roots, and in the case of the smaller of the two primes, twice the square root. So for 65,027, the continued fraction terms are alternately 255 and 510. With plots like this, you need to scramble the sequence to get a good coverage when you are doing high dimensional integration or high dimensional simulation. Otherwise, those two dimensions will just go along the straight line and not give you good coverage. There are several different ways that have been used to scramble the sequences. Richtmyer is not much used, and I think that after seeing how scrambled Richtmyer behaves as compared to scrambled Halton, you'll see why. So, since it's not much used, I made up some scrambling methods myself. Now, scrambling is done by passing all the coordinates through scrambling functions. This is no scrambling, so the scrambling function is the identity. Quadloads computes the Richtmyer sequence by approximating the quadratic irrational with a rational number with large numerator and denominator computed from its continued fraction representation. So, in the case of the prime 5, it uses 2 consecutive Fibonacci numbers. The third scrambling is computed by exclusive ORing the numerator with a number ending 010101, which is negative 1/3 in the 2 adic numbers. And this is what its scrambling function looks like. If you change the prime, the denominator changes, thus making the scrambling function look somewhat different, but it's essentially the same. This part is done this way to make sure that exclusive ORing the numerator with 01010101 does not produce a number that exceeds the denominator. Do Morse scrambling is done by exclusive ORing the numerator with the number ending 1001, 0110, 0110, 1001, called the do Morse word. And gray scrambling, whose scrambling function looks quite different, is done by taking the inverse gray code of the numerator. Now I'll show you what these look like as a scatter plot. Well, a scatter plot of unscrambled is a straight line. Scatter plot of third scrambling looks like a bunch of blotches. So does G Morse, and so does gray. They look like different patterns of blotches, but they do not cover well. Scrambling the Halton sequence, there are several methods of scrambling out there, some of which I could not easily extend to primes up to 65,000 something. But one that is commonly used is the 4 scrambling. And this is what its scrambling function looks like. The way the 4 scrambling is done is you take the if the number is odd, you take the middle number that is halfway between 0 and p minus 1. Of course, if p is not 2, it is odd. But the 4 scrambling is defined for all positive integers, not just primes. And you split the 4 quadrants and move them apart just enough to put a point in the middle. Otherwise, you if the number is even, you take the 4 scrambling for 1/2 the number and replicate it in in such a way that it looks somewhat like the Halton sequence for 2. So here's the flower plot of the Halton sequence of 2. And here is a full scrambled sequence for a large prime number. They look very similar. In fact, the flower plots of full scrambled Halton for 2 close prime numbers look almost identical. This is a problem because when you plot one against the other, okay, what happened? Oh, only 4,096. Can't see the pattern until you get more points. So this is what the scatter plot of 65,027 versus 65,029 full scrambled looks like. A bunch of diagonal lines. Not very good coverage. And similarly for the other pairs of twin primes, they all look like bunches of diagonal lines. Another way to scramble them is to raise them to a large power modulo the prime number. This is something I came up with for quadloads. I raised the digit to an exponent near the prime number divided by phi. This, for large prime numbers, produces a pattern close to random, which is easiest to see with the flower plot. This is the flower plot of 65,027 power scrambled. It looks like a random scattering of dots. Thus, 2 large primes, power scrambled, do not fill space better than random numbers would, which defeats the purpose of using a low discrepancy sequence. And this is what the scatter plot looks like. So for better scrambling, I came up with the Tipwich permutations. The Tipwich permutations are made by starting with 5, which is permuted. Let's see, scrambling function. 0, 1, 3, 2, 4. The permutations for 2 and 3 are the identity. Then subsequent permutations are generated by splitting the digits into 0, p minus 1, and 2 subsets. One increases by 1 for every new prime, and the other is the remainder. The Tipwich permutations for those two numbers, where the Tipwich permutation for composite is computed by factoring it and expressing the digit in the factors as if they were a base, then reversing them, and then turning the thing upside down, and then the two are interdigitated like the spikes on the margin of a Tipwich leaf, of a tippity-witchet leaf. Tipwich is shortened from tippity-witchet. This produces sequences that are low discrepancy, produced by interleaving two low discrepancy sequences, and thus the flower plots of two close together prime numbers look quite different. And they don't look like random scattering either. So a scatter plot of two close together prime numbers fills the space pretty evenly. It may not look more even than the random numbers, but it is, and to see better, I would have to go to more than 65,000 points, because I'm using two primes that are just a bit less than 65,536. So here is Tipwich, here is power. Now you've seen that low discrepancy sequences are connected to several other areas of math, and you've seen some of the scrambling methods.